That just says we're live. Yeah, I just muted you, and now it won't let me. I muted you to see if I could mute and unmute you. And now you're unmuted again. Anything? Sing a song. Do you know any Gilbert and Sullivan? I am the very model of a modern major general life information vegetable. No, just me. Yeah, just me. I mean, unfortunately, Lisa, you now get the classic turn off your computer and turn it back on again. Just make sure everything's plugged in when you turn it back on. Bye. Hi, everyone else. How you guys doing?
Hi. Good.
Oh, good. So is everyone full of questions, or you just want me to blather on? No questions? Okay, bye. It was fun. See you later.
No, I have questions, but I don't know how to ask it.
No,
the test
we don't get
house,
questions.
they just fell and cancel everything static. So it was like, okay.
Sad.
Yeah, I guess I have to do it again. But so the test is really have to work with the stall. So I have to do the test and then do all the chemical analysis and to see what's happening.
Right. So now we're at the point where you can look at what you've got and play with it on stall and really start to give yourself some perspective as to what was going on in your glaze, what is going on in your glaze. Because that's the fun thing. Do you have your formula real quick? Let me see if I can pull up your formula. Fast. Because that's really the fun thing of going back and looking at like what happened in the first lab, right, where you start taking stuff out, and now we can go back and look at that in relation to stall. And now all of a sudden things start to get sort of cool, because now we can put a perspective on what was actually happening. I'm trying to find where you had posted your results. I'm not seeing them.
Okay, can you hear me now?
Ah, there you are. The ultimate in tech support. Turn it off, turn it back on again. Quan, do you remember what video you posted in?
I think in Canvas. No, the first one or the second one? The first one is in Canvas, and the second one is...
Oh, that's right. You were in Canvas with that one.
Yes.
That's right. I was looking for a number sequence. That's the problem. That's right. So you are here.
So, but I posted third test on...
Gotcha. Yeah. So let's see. Lab 1. There we go. Okay, so now hold on. Let me put your formula into a calculator, and we'll have a little bit of fun. So Nefsi 56, Whiting 20. Oops. Kaolin 6. That's 18. 18 and 6. Now you actually had an anomaly in your formula, because before we got deep, and we're sort of picking formulas before you realize what's going on, you have zinc listed as a colorant. Of course, now we know that zinc is an RO flux. But okay, so we're just looking at a formula and sort of going back and reimagining sort of what we saw in the first lab. Now here is, let's see, so these are Quan's original tests. Okay, so if I remember, you pulled this off of Glazy.
Yes.
Okay, so we'll look at the formula here in a second. But we've got an original, sort of a beige. It's a little blown out on here, but a beige matte, and then without feldspar, clay, flint, and carbonate. Of course, then the fascinating thing that we now know that we can do is we can start to break down this formula and look at what is actually happening as we remove those ingredients. Because from a UMF perspective, all of a sudden, our understanding and perception changes. Now, I'm just not going to talk about the colorant at this point. She's got rutile, which is giving her, sort of beiges and tans, which is what rutile will do. It's not particularly dynamic as a colorant outside of atmosphere, but, nice enough color palette. Rutile does have one anomalistic behavior, which it will make sometimes glazes that shouldn't be matte into something resembling a matte glaze. Okay, we've got this phase separation thing that goes on with rutile, but not particularly important because where she's starting with is already a matte glaze. Okay, so this is just the formula here. NEFSI 56, whiting 20, EPK 18, flint 6, and zinc 9. Now, in her results, again, there's one slight little anomaly because did you ever take out the zinc, or did they all have zinc? I think they all had zinc, if I'm not mistaken.
They all. Yeah.
Okay. So again, just live and learn, not a big deal, but we can start taking out ingredients and see what it's doing. So, you start with the NEFSI, and now things get really funky. All alkali earth. Okay, that's to be expected. The alumina level drops down. The alumina level drops down. The silica level drops down really far. I'll talk about why in a second. I should go back. Actually, I'm jumping ahead. We didn't even look at the original glaze. 4.5 to 1, right? 0.3 to 0.7. Again, this is a glaze that she found on Glazy. I didn't have anything to do with. And it looks like a nice matte glaze. I mean, does that seem accurate, Kwon? Yeah.
Yeah.
Great, nice. Yeah, it's a very nice matte glaze. Were you doing this at 6 though?
Yeah, in cone 6. I'm planning to do a test to move it to cone 10. So just adding a little bit more like silica and alumina to move it up.
Well, you also have a funny little anomaly that I don't talk about in Glazes 1. But in Glazes 2 comes up that actually small amounts of zinc is one other way of bringing down temperature, which is a funny little anomaly that zinc does, and it's a slightly more advanced topic, but it's quite all right. So 4.5 to 1, we're within the matte region of Stull. It's a matte glaze. It's perfectly fine. So again, take out that NEFSI. Now, the first thing that we have to understand that goes on with the math at this point is that our silica and alumina levels drop through the floor. Can anyone tell me why?
Because the NEFSI contains silica and alumina?
Absolutely. The NEFSI contains silica and aluminum, quite a lot of it. Okay. Also, by removing the NEFSI, okay, we've only got one flux left in this glaze. Okay, and that's in the form of whiting, and of course also the addition of zinc. By having what is essentially a lot more alkaline earth flux that has no silica and alumina attached to it, because remember, whiting is just calcium carbonate, that proportionally drops the total amount of silica and alumina, which now puts our glaze all the way down here. Okay, so now I'll go back and reverse that. This is with the NEFSI bringing in silica and alumina, as Kevin's saying, and then without, and it's just dropping all the way to the floor. Now, this has got some benefits, and it's got some problems. This is definitely falling in that sketchy area as far as, what I would say of the conditions of sort of good glazes, hate to say bad glazes, but what is interesting is that this glaze all of a sudden becomes very interesting, to say the least. Okay, this is one where you're really getting a radically different effect with the all RO. Your color palette has certainly changed, okay, to a larger degree. You've also now got speckling going on in here.
Mhm.
And what is going on is that this lower region of Stull, we have to remember, is where chaos begins to ensue. The rules about matte versus gloss really start to fall apart under 0.3 Illumina. Okay. Now, there's a lot of reasons for that. Again, it's sort of a complex subject to discuss at this point, but we can go back and reference in the special effect glazes. This is where the fake wood ash glazes will happen. And then there's this other condition that I talk about a little bit with this concept of phase separation, which is where you get two different types of glass happening within one composition. And you really get a lot of it when you're sort of under 0.3 Illumina. Now, here's the thing. It's pretty hard to get down to 0.3 Illumina because of what happens with this. If I just make EPK and whiting, right? If I remove any clay or any flint, and I make this 66 and I make this 33. Okay, now, oops, I have 0.3 to 0.7, okay, and I have an Illumina level of 0.3. Having a 0.3 to 0.7 flux ratio, I cannot go beneath this 0.3 Illumina level, right?
Mhm.
Because where would I take Illumina away from this glaze? I can't. Okay. Now I could reduce the amount of Psi, right? I can take this down to, let's just say 40. Okay. Now my Illumina level has definitely gone down, but my flux ratio has also changed. Okay. So if I want 0.3 to 0.7, literally as low I can go is 0.3 Illumina. Now I can then come in, but then this isn't even a particularly good glaze because there's no clay to keep it suspended. I need my 10% clay. Oops. So if I take EPK and I plug in 10% clay, well, that's going to make my base level Illumina at 0.37, meaning that's as low as I can go and still have a functioning glaze. Okay. So here, so instead of Stull being this whole big thing that we're looking at, Stull really is a square that goes from here around to here, right? Because we also know this stuff up here won't melt. So really, Stull becomes much smaller when we deal with what our materials provide us. So there are ways that you can get down into this area, but should you, what is the benefit of that? That becomes a little bit of a question. Now for this as an experiment of just going, hey, what happens when I take out certain materials, that's pretty cool. And the result that you get is pretty cool. Right.
Yeah.
But is it necessarily a functional glaze? I would not put it on a food surface. I'll tell you that. Could you use it on an exterior? Sure, absolutely. Could you use it on a sculpture? Knock yourself out. But, does it meet the conditions of a highly functional glaze? No.
So this,
Go ahead.
This effect only happen in that part of Stull. So if anything I do, I will just lose this effect. Like trying to improve the glaze is just losing this special effect that happened only in that specific area.
Well, yes, for the most part. Okay. Again, this becomes a sort of more advanced topic, but the lower corner of Stull is sort of where a lot of the craziness and the magic sort of happens. But there are glazes that aren't necessarily what you should be doing. But you can make glazes there. It's just a question of how. Because again, when we come back down to this condition of, I can't make a glaze under 0.3 to 0.7. Well, what are you going to do to get down here? You can do what you've got going on, which is, something that's basically all alkali metal, very little alkali earth. The alternative is you can start to use a soluble material, which, is debatable. So if you come in here and you plug in soda ash, right? If you make this 10% soda ash, now my flux ratio is getting out of whack. So I have to bring up my alkaline earth again. So I'm going to make my whiting 50. So now I'm back at 0.3 to 0.7. And now my alumina level is dropping because I'm bringing in an alkaline metal that doesn't have any silica or alumina attached to it. But it's soda ash, and I can keep going. I can make this 20. Again, I have to bring up my whiting to correspond to that, make that 60. It's not even enough. Make that 70. So now I'm getting down into this region, but I've got a glaze that's 12% soda ash. I mean, that is just studio problems all day long. So you don't really want to be doing that anyway, unless you're going for this very specific effect. But, you've already found what that effect is. It's this glaze. And can you use it? Yeah, you can use it. Again, I wouldn't put it on a food surface, but it's definitely a very interesting glaze. It's, something related to the fake wood ash and all of that, which remember is all alkaline earth, very little silicon alumina. You're not getting the rivulets quite where you are. I suspect it's because of the behavior of the zinc, but again, you are getting, this beautiful crystallization that's happening in here. Definitely nice effect. And that's why you're also getting the rutile in the crystals is why you get the two different colors going on, because the crystals will pick up rutile and iron, or the titanium and iron differently. So it gives you these two different effects. And it's a beautiful, very buttery sculptural glaze. Just depends on your context of what you're looking for. So coming back.
Did you say that you were that you fired that in cone 6?
Yeah.
So I guess what would happen if you fired that in cone 10?
Yeah, I'd like to try. I think will it be running or
It'll probably run.
yeah.
So
like I said, go ahead.
Is zinc kind of acting in the same way as boron does, like in lower temperature?
Right. So again, this is sort of an advanced subject that I try to dance around, but there is a type of glaze called a Bristol glaze, which is a high or not even high zinc. It is a glaze that contains a certain proportion of zinc. And that zinc in combination of usually calcium will make a slightly lower temperature melt. And so unfortunately, so now that we're at the end of Glazes 1, I can tell you that Glazes 2 is all about me being a hypocrite and going against all the things I just taught you in Glazes 1. Because Glazes 2 is all about the anomalies and the weird things that happen. Because no matter how much rules are wonderful, there's always going to be anomalies, and having a small portion of zinc is one of those. So, and actually, I've got one of my more advanced students is currently trying to make even weirder glazes happen at Cone 04. But, he's just crazy. But fun, but crazy. So bringing this back to 56, right? And again, all the rules of Stull still apply, even with the zinc thing. It's just affecting the temperature. So it's not, it's not anything magical. It's just the temperature. Now, of course, you could ask the question of, well, why don't you do this for all glazes? Well, zinc becomes a very dominating flux when we talk about the effect of color and texture. Zinc only gives you a very limited color palette. We sort of talked about that, of the whole zinc MgO relationship. So it's not a very good solution for getting a lower temperature down, unless you happen to be working with this sort of white buttery glaze as it is. I want to take your next one, and you had no clay, right? As your next image, if I can. Right, so without clay, again, a little hard to see. It's blown out, but I see it looks like a gloss with crazing. Is that accurate?
Yes.
Okay, so we now have gone from a matte to a gloss with crazing. The color palette looks somewhat similar, not completely dissimilar. And all of a sudden we are glossy and crazing. Well, shockingly enough, when we come back to the formula without the clay, well, now our flux ratio has flipped to the other side of the matte line.
Yeah.
Okay, so your glaze is gone from matte, as you would expect, to glossy, as you would expect. You're having some glaze fit issues. Did did the original glaze craze as well?
No.
I couldn't see. No. So
Only
now, right. So now we've moved into the crazing region, which again is based on the relationship of her clay and her glaze, all of that kind of thing. The alumina level is reduced, the silica level is reduced, but the ratio has flipped a little bit. And there you go. I mean, we didn't touch her fluxes, so the fluxes are essentially the same. And, we're just moving around Stull, right? Here we go. There's the original, and there it is without in the original. So now, the crazing region, again, is always dictated by your clay body. So on this clay body, this is not the crazing region up here, but as soon as I take that clay out, right, now you're well into the crazing region and you're into the gloss region, and lo and behold, that's exactly what you get. This is why I love this experiment, because, for the most part, it's very predictable. There are anomalies like taking out the feldspar, and we can look at Jeff's in a bit. He posted some earlier, and you start to see those anomalies, but big fun. And again, proving I'm not completely full of it. Taking out the flint is not as big of a jump, because all we're doing is moving in more into the matte region and coming back to the original glaze. Looks like it's more matte. Is that accurate? Yeah. Right. Yeah. So it's more matte. And that's the manipulation that you have of controlling the level of matteness based on what's your flux ratio. Okay. So by taking your flux ratio down, we're now at just under 4:1. It's more matte. Now it's not the original glaze, and maybe you like the buttery one more, and so you go and put that flint back. It's only 6%, 5.5%, but it's enough to nudge it and see how you affect matteness moving inside the matte region of Stull. Again, totally predictable and totally beautiful. The last one that you have that I didn't show yet is to take out all the whiting. Okay. Now yours is, again, this is where yours is going to be slightly opening, too many clicking wrong buttons. Yours is slightly an anomaly, okay, because you still have the zinc in there. You only took out the calcium. So for somebody else, if they removed all of the alkaline earth, it would be a slightly different result, but so here, you're still at 5:1, but what's really going on is your alumina level has just shot up. Okay. Your alumina and your silica level. Your ratio stays the same, but really you're becoming underfired. You just have way too much silica and alumina to melt at this temperature. And shockingly enough, this looks sort of melted, but mostly underfired. Is that an accurate assessment?
I'm not quite sure. It's a little bit shiny and with pinholes on it. I don't know. It looks quite different from the others. So
right, and that, I mean, again, well, you can see that Stull tells us it's very different. It's a little bit shiny, but if you were to do a test where this actually, an interesting thing you could do if you wanted to keep playing with this is start taking out clay, right, and maybe a little bit of flint. So there, I mean, I just cut the clay level in half, cut the flint down to 6. Right, so now I dropped 0.1 alumina, 0.12 alumina. It was at 0.85. Now we're at 0.73. If you made this variation right here, you would find that it is more melted. Okay. But there are things to watch out for. The first is that you're talking about that it's pinholed. Well, shocking enough, it has a lot of clay in it now. Right? So, you've gone from your original formula, which was 16% clay. You've gone up to 22% clay. The other thing is that your alkali metal level is climbing, which is going to help it flux. So basically, if I was to remove all the zinc as well, right, all of a sudden you've got a Shino. Okay, remember, Shinos are 1.0 alkali metal and a lot of clay. This is 1.0 alkali metal and a lot of clay. You just happen, since you had the zinc in there and we're accounting for it differently, it doesn't quite go to that extreme. But what this is now halfway to a Shino. You've got an elevated alkali metal level. You've got a ton of clay. And that's sort of what you're showing here. It's Shino-esque. If you wanted to push this more towards a Shino, again, you could take the zinc and say, cut that in half, make it 5, Oops. So why didn't that adjust? Huh. What happened? Oh, it's reached the max. Sorry, the map won't go up that high. Again, a very interesting result, a very predictable result. As with the Shinos, now, one again, an anomaly that comes up here is that this is clearly in the semi-matte region. And it, like you said, it's still a little bit glossy. Well, if you recall, let me open up the appropriate file. Special effects. Right, when we start to look at the analysis of Shinos, oops, way too far. The collected Glazes analysis, they're all within actually the semi-matte range, but they're not semi-matte, and that's purely because as you push the R2O levels that high, the matte line sort of disappears. And for these glazes, it tends to be clay and feldspar for the most part, doesn't have any alkaline earth, and it very rarely has any flint. Of course, if you had flint, you'd be moving over here more, and what would actually happen is that the glazes would start to dry up. You just have a ton of silica, a ton of alumina, and it doesn't work. Whereas most of the Shino formulas are really just these 3 ingredients. You'll get Nephsi, and really it's 2 ingredients, Nephsi, soda ash, and OM4. So a feldspar, a carbonate, and a clay. And, Shino formulas tend to be bordering on just that simple, and again, we could make up a straight Shino here by just messing around. You just delete that. I mean, there you go. That's basically a Shino. Can add in soda ash.
But the Shino doesn't seem. The Shino seems to be shiny, even though it's in the matte area.
Right, and it is. We just switch this to OM4, and we're really just using OM4 because it's got more iron and titanium. So if I make this 80, so the clay level's a little bit high. I can take this down. Well, no, that's fine. I can add in 10 soda ash, and then I can bring up the clay level higher, 20, 30. So seriously, like that's a Shino, right there. It's in the semi-matte region. A little bit of soda ash. The soda ash helps in the Shinos because you're bringing in carbon trapping. I talked about that in that lecture. I mean, it's again, these basic trends. It sort of doesn't matter what the formulas are, that these trends really continue. That's why I love this first lab so much, because, at first it's like, oh, that's a really interesting sort of result. Oh, that's weird. And then when we come full circle to the end of the class and we can really see, oh, this is bordering on fake wood ash. This is bordering on Shino. Oh, it becomes matte when I take the flint out. Oh, all of these types of variables, and they're all pretty predictable. And we start to see how flexible our materials are. So things like, what fluxes you're choosing and why you're choosing them, how they affect your colorants, where you're trying to get your textures, all of those things become very, very important variables that you now have control over. So what was this at 20, right? So coming just back down to your original formula, that, all those variations are buried in there. It's all the sort of the special effects, the fake wood ash and the Shino and all of that. You don't have the fake wood ash effect, but you're not sort of, what did I say? Take that out. No, your silica alumina levels are still a little high. If I came, where's my thing? If I came and looked at Glazes real fast, and I just said fake. So yeah, see, this one's got its alumina level down to 0.22. So again, you're pushing that alumina level down as far as you can get. Again, basically all RO, very little R2O. I can go back and pull up at the formula here in a second. But, again, since Glazes showing us the related formulas, fake ash, fake ash, fake ash, Albany drip, fake ash. And because they're all very low silicon alumina, and all RO. Pull up that one real fast. Yeah, I mean it's there we go. Red art and whiting. That's all it takes. Red art and whiting together puts an alumina level at 0.2. This is bringing in iron. I think it said it was red. And again, they all just fall within that trend. So you're probably a little high quite to get the fake wood ash effect. Plus the zinc. I don't know how the zinc is affecting that, but, pretty predictable as far as the result.
Mm-hmm.
Any questions on that one? Beautiful set of tests, Quan. Beautiful.
Thank you. I'm very happy with this one. I think I can continue with this one to explore more about the materials. And I don't know. I tried the second one to replace naphthite with the feldspar, soda feldspar, and potash feldspar, but they have very different results. So I don't know if naphthite has to do a lot in this glaze.
It could be. Well, it depends on what your supplies of those feldspars are, and I don't know what you're getting over in Hong Kong as well. But we can. Well, we'll look at some other results, and we can talk about that. Jeff, can I put you on the hot seat?
Yeah, let's talk about mine.
Let's talk about yours. Let's see. Is this one or is this? There's one. Okay.
There's one.
Let me zoom in a little bit.
If you click on it, it does too. You get
right.
res one. So, it's starting to clear up. So, I mean, the first one, the Scotch Red without silica, I was surprised by that one because, I mean, I read that if you lower silica, it starts to feel like it doesn't. The texture doesn't feel as glassy, and I guess that's because their silica is the glass. So, is there another reason for that, or is there a reason to drift?
Second. Let's go before. Let me pull up an analysis on here.
Oh yeah, sorry. Hey, and the silica or the flux ratio is not ideal, so it's up like a 0.1.
I don't care. I don't care about ideal. I just like seeing what's happening. Yeah. I didn't say to search for an ideal formula when we started.
Yeah.
With this, so, okay, let's make sure. Okay, so here's the formula from Glazes. So silica Gersley again. Now it's a little bit more complicated because you've got some extra.
Yeah, sorry.
Here. No, it's. I mostly say it for the ease of my sanity, because what'll happen is as we start to get into stuff, people say, "Oh, but what about this? What about this?" And I go, "Well, you've got an anomaly there, but now we're at this point where we can talk about it." So silica Gersley whiting, nephsi EPK, and chrome in tin. So it's really a chrome tin pink / raspberry, which we can talk about in a second. Here's the Glazes analysis. 0.23 alumina, 0.24 boron, 2.43 silica at a 10.5 to 1. And as you said, it's a 0.14 to 0.86. So nothing about it is inherently ideal. It's not terrible. But what I'm going to do is I'm going to move off of Glazes and I'm going to plug this into the calculator here. Give me 1 second. Talk amongst yourselves. Anybody got any good stories?
Well, I should say that the color looks pretty good of the base glaze. I shouldn't say base. The base plus the colorants looks really good.
Right.
And it came out pretty good. I fired it at cone 5. It's a cone 5 to cone 6 glaze. And then when I removed the colorants, it stayed a little bit cloudy, but it still was all right. It wasn't a perfect clear.
Okay, I think I've got this. Wait, no. 21. Oh, no, Neff size 16. There we go. How I'm in long. Okay. So, let's see. Go for it. Talk to me.
So, first, let's look at the first one is the without silica.
Yeah.
On the top left. So you see on the right are the standard and the standard without colorants. Oh, I spelled that wrong, but that's okay.
That's okay.
So, so Scott's red minus silica is the top one. And you can't see it very well, but on the far left, you can see where it started to pool.
Yep, it's got a pool.
And then it also has some little cracks in it or dots that look like bubbles or something that were
Like
near the
this?
surface. On the left.
Or down here.
Yeah, in that bubble.
Right.
And then you can't see it real well, but along the top, it looks crinkly, which is something I'd never seen before. It looks like it looks like a piece of clothing that's been kind of squished together.
Actually, we have seen it in the class, in that slide in glaze flaws of the world's oddest glaze flaw. It's it's along that line. But let's just go through the analysis real quick. Okay, so with this formula, right? Here's the original formula. Again, the magic of the math. I take out the flint, and your glossy glaze is now in the matte region. So it's actually, by taking out the flint, it's not. I think you sort of started to say it was drying up. But it's not drying up. It's becoming a matte glaze.
Oh, okay.
Right? Very simply.
That's what it should do.
Right. It's exactly what it should do. You went from here, I can flip it back. You went from a 10 to 1. My analysis is slightly different than Derek's. I think his is 10.5. Mine's 10.8. And you're 32% flint. That's a massive amount of flint. And again, by pulling out flint, we just move to the left on stall. Oops. Right? And boom, you're in the matte region. And again, there you go. Matte glaze. And we know it's a true matte glaze because of the running. Okay? Because a true matte glaze can run. Because it's crystals growing in a glass. The glass can run. And what you're seeing, and along with the crinkles up here, are actually a result of the matte being a very solid blanket of crystals, but the glass underneath it running. And what that does is it removes a little bit of the structural integrity under the glass, and it makes that wrinkle effect. And you guys can't really see it. I can pull it up in the world's oddest glaze.
Is it kind of like a lava flow with the cooled surface?
Exactly. Great analogy, Lisa.
So
it's here, right? So this chicken skinning right here, this is exactly the same effect. The crystals are a solid blanket, but the gloss underneath it is moving.
it almost looks in this one like the crystals were the part that sagged rather than the gloss underneath.
Well, the blanket of crystals does begin to sag and then contracts on cooling.
Okay. And then when do the crystals don't form on the way up, right? They form on the way
down. Once you've got your glass, they precipitate out of the glass.
Probably near the peak, or
yeah. As soon as the kiln starts to cool, the crystals start forming until the viscosity of the glass is high enough that it can no longer precipitate crystals, and then the glass seizes up and forms the amorphous solid that is a glaze. Remember, it's not a supercooled liquid; it's an amorphous solid. So yeah, this is again sort of going through what we'd expect. Like that's a perfect result, you know. That's a beautiful result right there.
Perfect.
And then, okay, so let's put the flint back and let's knock out the Gerstley borate.
Well, this had the effect of reducing the boron, and the boron is what made it a cone 6 glaze. And my guess is that it's probably now closer to cone 10, and so I didn't go that hot. That's why it looks so false matte.
It is just dry. And as you said, if you fire this to cone 10, it would probably work about just fine. You can even see that there's no color. Why is there no color? Because there's no glass, and the colorant needs the glass matrix to create its color.
Yeah.
And so, again, since you have Gerstley and not all these glazes have Gerstley, this is an anomaly you're not going to see in everyone's glazes. But, coming back here, your silicon alumina levels went up. Your boron level went down. I can switch it back and forth again, right? Your silicon alumina levels, your alumina went up almost 0.1, right? Your boron went down to 0. And so it's nothing, as you'd expect. It's just underfired. And exactly as you say, if you fired this to 10, it would probably work just fine. Silica level still a tad high. If you really wanted to make this work at cone 10, I'd probably take that down to 20. Or that even might be a little bit extreme, but again, it's exactly what you'd expect.
Yeah.
Hey, Matt, can I ask you a question about that? So if the second tile there that is underfired, so say he went back and refired it to cone 10, is anything everything's okay as far as the melting process? You can put it back in there and fire it higher and it'll be fine, or has something changed in the process?
You're just talking about
just the mechanics of firing it again.
Of refiring?
Yeah.
So refiring can be tricky, and it depends on the composition. A lot of times people have the refire, which you have to understand is when we're firing, right, you fire, nothing happens until those last 6 to 8 cones. Then everything starts melting, and then you shut off the kiln plus or minus a soak, and then it cools. When you refire, what you have to understand is that as soon as the glaze starts melting again, it's actively melting any material that is left undissolved. And so to some degree, that can change exactly what is going to happen in the glaze. For the most part, it's fine. For the most part, you won't see any effect. Sometimes colors can be affected because the way they're incorporated into whatever glass matrix exists. But for the most part, yes, refiring is fine. But you can say get a lot of running refiring a piece. Okay, because as it starts melting, instead of using its energy to melt silica and alumina, which is what's going on as the temperature increases in a first firing, now theoretically all that silica and alumina is melted. So what happens in the viscosity of the glaze is that the viscosity can start to drop because it doesn't have any energy any silicon alumina to melt, which is going to, let's say, for lack of a better term, distract the glaze from running. But if the silicon alumina is melted and the temperature keeps climbing, it could run. But for the most part, it should be okay in general, especially with this one where it never melted in the first place. That sort of doesn't apply. But if you're talking about a glaze that's been to temperature and then is refired, it could happen. But for the most part, no, I wouldn't worry about it.
Let me ask you another temperature-related question real quick.
Absolutely.
Do cones age? Like if you refire an old conometric, Orton cone, and you don't melt it enough the first time, like the second time, is it still pretty accurate?
No, don't reuse a cone.
Okay.
There's don't reuse a cone because of exactly what I'm talking about. A cone is based on the dissolving of the silica and alumina inside that cone melting at a constant rate. If you're refiring a cone, some of that silicon alumina has melted and it's going to change the temperature.
Right.
Then there's the question of just old cones, as in this cone has been sitting around for 40 years. Can I use it? The answer is, from a chemistry perspective, yes. But sometimes, because cones, remember, they are just feldspar, whiting, clay, and quartz. They are just glaze ingredients that sometimes the cone, by becoming completely dry, will begin to fall apart. So they could crack and break and all of those types of problems. And it's the same problem with concrete. If you know about concrete, that concrete is actually completely useless when it's completely dry. When it's cured, it takes like 100 years for that to happen, but it actually becomes very physically weak. It needs that constant source of water in there to keep the reaction going slowly. Okay, so let's see. Popping out. So we've got without kaolin, right?
Yeah, I wasn't sure about this one.
Oh, what's not to be sure?
Well, it turned foggy.
Right.
And
it turned foggy. Your silicon alumina levels have gone way down. It looks like it really became matte. Is that accurate, or is it just underfired?
it feels very smooth. I would think that taking out kaolin would make it easier to fire.
Yes, but
I don't
now
know.
you're falling into this area that we were just talking about with Quan, that you're in the funky region.
Yeah.
I mean, look at where this glaze is falling. I mean, it's so little silicon alumina. You're really in this area where the rules don't apply. And probably I would say actually to a certain degree that the fogginess is coming from undissolved silica.
Mm-hmm.
Because now, again, something we haven't really talked about a lot is, okay, so you've got this whole region of Stull here that says under fire, and that still says that at 0.1, 0.15, 0.2 alumina, very, very low alumina levels, because you can still have too much silica on its own.
Mm-hmm.
So even though the alumina level is exceptionally low, you can still have too much silica and it won't melt. Okay. And so most likely the fogginess is coming from undissolved silica.
Mm-hmm.
If there's any matteness to it, I would bet that that's undissolved silica too.
Okay.
You know, this is not a good composition, you know, as far as I would say, but you know,
yeah,
to each their own.
Cool.
So going down, I got to stop opening those. Let's see. Going down the list, we've got without Nef Psi.
I have a question about the second tile.
Sure, Michelle. What's up?
So when you plotted that on Stull, it
Mhm.
was on in the gloss region, no?
Right. Absolutely. Great question.
So then how come, if Stull dictates that, then how come it didn't come out glossy?
Because this is a cone 6 glaze. Okay. And so you have to go back to remember the rules of cone 6. And that the big rule is you need boron. Okay. By taking out Gersley,
right.
Now there's no boron. And so if this was a higher temperature, should totally melt. But without boron, it's just underfired. So not much changes. I mean, I'll put back the Gersley. Not a heck of a lot changes, but two things did happen. One, we brought in boron. And two, the silica and alumina level actually goes up when I take the boron out. You can watch it again. Oops, wrong button. There we go. So the silicon alumina level goes up. That raises the temperature. You take the boron out. That raises the temperature. Make sense?
Yeah.
Okay, so what were we doing? No Nef Psi?
Yeah. The no Nef Psi looks a little bit matte too.
And again, I mean, it's basically the same problem, except that you've got all alkaline earth. Okay. But you're still in a fairly high silica level. If we went back, do I still have the tab open? With, no, I don't. Where did I put that? With all those fake wood ashes on Glazy. No, they're gone. Anyway, that they tend to be more on the matte side of the map. So over here. Right. And you've just got too much silica. So it's underfired, probably resembling matte. You're getting some of the more of this haziness in the glaze. So it's just inherently underfired.
Yeah.
And
Okay.
then for the piece de resistance, taking out the whiting. Again, now really high silicon alumina levels for cone 6, still a fairly high silica to alumina ratio. The catch is actually your flux ratio is not that far out of whack, because along sort of what was happening with Quan, that Guernsey borate is mostly a calcium source. You're mostly bringing in boron and calcium. So you still have a fair amount of calcium in here. So it didn't go, say, in the Shino direction, but it also didn't melt. Okay. You have a lot of silicon alumina up here, especially a lot of silica. Is it melting at all? I can't quite tell.
It's actually melting pretty well.
It is melting.
It feels as smooth as the only one that's just as smooth is my Scots Red.
The original.
Is that a good? Yeah, the original.
Well,
is that a good indicator? Just this, like rubbing my hand on it.
It's not
whether or not it's melt. Whether or not it's matte, or
it's not a terrible indicator. Actually, the best indicator that I really like with determining whether or not glazes are working, whether they're true mattes or false mattes, is start adding and removing silica from a glaze and seeing what happens. I believe I mentioned this in class, but if you've got a true matte glaze, which falls over here, and you add silica into that glaze, it'll automatically become glossy. Okay. You add silica, it becomes glossy. You're here, you add silica, it becomes glossy. The same with this. You could take silica, say, out of this formula, and it should actually become a true matte. So say you take out half of the silica. So if you're at 32, if I just make that 15, it should become more glossy. And you can determine the validity of your glaze by just messing with flint, just the one ingredient. And as glazes tend to have a lot of flint, it gives you a lot of that variability. Okay, I can see that that's melting. Your flux ratio is not perfect, but it's mostly on point. Your boron level is fairly high. I would say for durability standards, your boron level's a little high and your alkali metals are a little high. But yeah, I can certainly see how, go back to the original. Yeah, I can see how that's melting, that's not that out of whack. Now you're not getting your color, which again goes back to the role of the alkaline earths in color.
Yeah.
Okay. Colors are all about the alkaline earths. That's really what more than saying, oh, well, cobalt makes blue and chrome makes green. That's what I really want you guys to learn from the final color lecture, is that it has a lot more to do with the alkaline earth, giving you color than anything. So we come back to this. Hey, you remove your alkaline earth and you don't get the same color. Whereas here, red, 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 red. This is just underfired, but no alkaline earth, no color.
Yeah.
Very cool.
Yeah, that surprised me. I mean, I'd read that it was going to be different, but when I saw it, it was pretty dramatic.
Well, where, did I save them, or are they all still? I was going to pull up another class's test, which I shouldn't do, but I don't see where I saved them. They're somewhere. I have too many files. But yeah, I mean, you see this across the board time after time. You get the same color, the same color, the same color. You take out the alkaline earth, and all of a sudden the color is completely and utterly different. Right? I guess I can pull up this.
So that's a good transition to lab 2, because
right
in my lab 2 pictures, you can see that it's swapping out.
They were in the same. Actually, they were in the same thread, weren't they?
Yeah. So.
Right. So
scroll down a little bit and click on the picture.
2. Okay.
So the ones where I switched out the calcium are the bottom 2, obviously.
Right.
And the one with zinc just sure turned into this buttery, beautiful glaze that looks mature, to me at least. It has a little bit of a funky texture, but it's not too noticeable. In fact, it would do really well.
Well, again, let's run the chemistry. I think that's your original formula. So if we just do a switch out for zinc. Now, again, You know, I do some slightly evil things, you know, when doing these, this lab too, because yeah, it's a straight up weight exchange. So now you guys also know that the weight exchange is not necessarily going to give you a consistent chemistry result, because some materials weigh more or less than others. You don't have a barium result, but the barium ones will often throw things out of whack. But yeah, so the zinc, you're now 0.56 zinc, where before you were all, 0.77 calcium, right? So now you've mostly got zinc. Everything else is basically the same. Pretty similar flux ratio. I think it's moved 0.02, if I'm remembering correctly. Your alumina level, your silica level, your ratio's down a little bit, but for the most part, they're about the same. But yeah, I mean, you come into this glaze and whole lot of nothing. You know,
Yeah, I mean, it was like I added no chrome.
Right. You're just not getting that color response. Yeah, you've got tin, nicely opacified, but the chrome is not going to do it. It's not going to carry through because it's all about that RO.
So what happened to the one without the Gersley? It didn't have color either.
It just never melted. It never had the chance to form color.
Okay.
If you look at it closely, it's still a haze of pink.
Yeah,
So
it's around the
edge, move in the right direction. Like if you look at the edges and stuff, it would mature, I think.
And that's because it's starting to form a little bit of glass, right? Make a little bit of color happen, but not enough to be substantial. And this has got two problems. One, zinc is just brutal on colors. You know, I talk about in the crawling glazes. The crawling glazes are so hard to get anything but the lightest pastels to come out of them. And a lot of heavy zinc glazes really react to color differently. And this one, yeah, it's just not going to make that chrome tin reaction. It's not going to let it happen. And again, remember the relationship between a lot of what zinc does, MgO also does. And, you know, talc is just an MgO source. And here we go. We switch it out for MgO. We're at 0.53 MgO. Silica alumina ratio has gone up a bit. The flux ratio has moved a little bit. Alumina has gone up a bit, but I mean, really minor tweaks and come back down. Same thing, somewhat melty glaze. You know, you got some pinholes, some application issues, but you know, other than that, it's a whole bunch of nothing. I mean, as far as this particular color response, I mean, the glaze itself could be interesting, you know, can't really say one way or another. Like you said, the zinc one is interesting. The silica level went up because remember talc is MgO and silica. So that changed the ratio a bit, but none of this really had a major chemical effect. Now you don't have a barium test, but again, like I said, barium will mess with things. So if I just went and did barium, right now the flux ratio is changed. The alumina level goes up, the silica level goes up, you know, things start to get a little bit more wacky, but you know, not that big of a deal.
What would you predict that would do to the color?
Well, I can't say I've ever tried a chrome tin pink with barium. I will say that the reaction in a chrome tin pink is not far off from a copper red type reaction where you're using the tin to influence the color. And, you know, I can say that in copper reds, barium makes them a little bit more bold. A lot of copper red people will use a fraction of barium, not the entire glazed barium, but a fraction barium to make them pretty bold. And then just to scroll up with these, from a color standpoint, you know, they're fairly similar. Not completely out of whack, but we can look at the chemistry in a second. But the color, again, we've got different levels of crystallization, but if you look at this edge pink here and the entire spectrum here, you're basically getting variations on the same color. Now, of course, you can say, oh, well, this has got this big white center, but, you know, we'll talk about that in a second. But for the most part, the color response is similar. It's not a major variation based on changing the R2O. So we've got Nefsi, so we go to Custer. Okay, silica to alumina ratio jumps way up because remember, really the difference between a feldspar and Nefsi is it's got a lot more silica on that molecule. The ratio stays the same, boron stays the same, alumina silica stays the same. It is again moving towards having a lot more unmelted silica, and again, this is looking bordering on unmelted to me. But Jeff, you can be the arbiter.
I don't know. How do I know? Like what I see, I mean,
Does
I'm not
it-
an electron microscope, so
Right.
I couldn't tell you for sure. To me, it looks like it's cloudy. Oh, but I think that's represented in what you see. When I feel the top of the glaze, it feels
Mhm.
very smooth and glass-like.
Mhm.
I
Yeah,
don't know what other
well,
adjectives.
and I
methods
guess
I have.
it's a good distinction because, I would say there's probably a decrease in total glossiness as compared to something with a lower silica level. But yeah, I mean, I have way too much experience and I take these things for granted. But again, you're getting this slight variation in color. I'm betting it's unmelted silica. Again, now you can verify that by taking your glaze at this point and, again, cutting your silica level in half and seeing what that does. Right. Or maybe even half is very high. Maybe you make it 25 and just nudge it back a little bit and see how that affects the entire system.
Mhm.
Because again,
If I had done lab 3, I might have gotten that result taking the original Scotch Red
right.
and adding more silica. It might look just like this.
And that's what lab 3 is literally taking out more and less silica and alumina only and seeing what it does. And then knocking out the rest of these. So we did the Custer and you did, was it Minspar?
Yeah, Minspar.
Right. Not a
Minspar is
huge
the same
change in
thing.
result. Okay.
So
Coming
it does
in
move
here,
left just a little bit.
it moves it left a
Yeah.
little bit. And this to me looks like it's melting a little bit more.
Yeah.
You're getting, this is either phase separation or it's just unmelted quartz. A little bit hard to say, but it looks more like phase separation. Again, you're down in that lower chaos region of Stull. So, neat effect, not the bold red that you got on the original glaze. But then we come down to spodumene.
And the spodumene looks almost just like the original glaze.
Right. Well, so the spodumene, the interesting thing is, okay, alkali metal ratio is about the same, boron level is about the same. What's happened is your alumina level has gone up, right? And this sort of goes back to what I was saying before of that, when you were down here, which test was it? When you're without the kaolin and you're really bordering on that underfired region and you've got this sort of the smoky haziness going on, okay, and I was saying that's just too much silica, even with very low alumina levels, that's too much silica to melt. Well, what the spodumene is actually doing, if I can pull up the right one, is that it's actually nudging you back towards the center. So it's giving you a more balanced amounts of silica and alumina together by bringing in more total alumina, which actually will make it melt slightly better. And that goes all the way back to talking about how the cones are working, that you really need to blend the silica and alumina together to really make it work. But yeah, like you said, it's somewhere near the original. Where's the original? Yeah, so you've got a little bit of phase separation. I'd almost say that the hold on, can I do this without freaking out my computer? Let's do this and then this side by side. No, don't go full screen. I want a side by side. Except they're backwards. So anyway, lab 2. Stop. Okay, so lab 2 on the left and lab 1 on the right. But yeah, so here's the spodumene. I don't know. I sort of like the spodumene one even a little bit better. The color looks a little bolder, at least by this
That
picture.
changed the flux ratio.
It
right?
did change the flux ratio because spodumene is a fairly low concentration flux. So we went down, okay? But you also have to remember that spodumene is a more active flux. So it's more, it's inducing a greater amount of melting. So, except I just skipped it. So you're moving 0.04 in either direction, okay, by switching between those two materials, right? Your alumina level is going up. Your silica to alumina ratio is going down. Again, so that's that very important consideration of, we haven't talked about a lot of glazes hanging out along this line, but, you know, I think that excess silica is killing the color to a little bit. And that the spodumene, you know, if I had to say, I lay these out. Ooh, oh, dope. Again, it could be the color, it could be your camera, it could be that. But to me, that the spodumene looks a little bit more dynamic. You know, relatively same color, relatively same hue and value, all of that. But, you know, punched up a little here, punched down a little bit there. But fun all around. I mean, you know, great results, everybody.
So let me ask you another question.
Sure.
Because glaze stability is important. So if I went up a little bit on my spodumene until my silica to alumina, or not my silica, until my my alkali metal came up a little bit.
Hold on, I was looking at the wrong analysis this whole time. There we go. The whiting. Oh, even better. Oh, even better. Look at that.
Oh, beautiful. Okay.
So the ratio went down, but your silicon alumina level, it just came more into the middle.
Yeah.
Okay, I was running that with talc if everybody wasn't watching what I just did. I forgot to switch it back to whiting. So switching it back to whiting, now the silicon alumina level is 9.3 to 1. So it's really just allowing more silicon alumina to bond together and leaving less unmelted silica. So beautiful result. Beautiful result.
But let's say I went up by 50% on my spodumene. And then because the spodumene has a good amount of silica, I'd have to go down on my flint a little bit to keep it. Well, that's pretty gloss too.
It's still pretty glossy. I mean, you're at cone 6. So, you know, a few things to remember. Your boron level is on the high side for cone 6. I wouldn't say it's concerningly high, but you've got well, did you say I think you said you did this to 5 originally, didn't you?
Yeah, it's actually 5. Yeah.
Okay, so at 5, you know, it's an adequate amount of boron. The ratio, I'm not crazy about it, but it's not terrible. It's, you know, as I say in the durability, it's not the end of the world. You know, you'll find plenty of glazes out there that are 0.15 to 8.5, so that's okay. You know, it's your ratio went down again. At a certain point, you're going to add silicon alumina and it will keep melting and actually getting glossier, which is part, although that this highest gloss here label is not right. It's also not wrong that actually you will get glossier as you add more silicon alumina because you're just forming more glass more adequately. So, but there will come a point where it will start to dry up. So say instead of doubling the spodumene so much, if say you're just adding clay, let's double your clay level, and then correspondingly add some more flint. That was too much. 37. Anyway, close enough. You know, so now we're at 0.43. You know, theoretically, this could be slightly more glossy than the previous version. Did I just say previous? I've been sick today. I've been sick all day. I just crawled out of my bed to come here. So, you know, it's worth trying. I couldn't say exactly what is going to happen by either of those changes. So we take those back. You know, you're sort of dancing on the head of a pin at this point as to what changes will do what before the glaze dries up. But, you know, keep pushing it and seeing where it goes.
So could you just take the Gersley out and then you've raised your temperature?
Pretty much.
Does it change? It didn't really move it, but now you can fire it to cone 10.
Well, it did move. Okay, that your alumina level, the alumina level here almost doubled. Let me go back and reverse it. Okay, not quite doubled, but we went from 0.34. No, that's not right either. 21. Okay, here's the original glaze. Okay. So we're at 0.28, and it goes up. You take the Gersley out, and it goes up to 0.4. What am I missing?
Well, the spodumene was not in the original recipe.
That was the original. That was the revised spodumene level. So I'm making too many changes as I dance around. Oh, you're just talking about the original formula?
Well, no, no, actually, I was interested in leaving the spodumene in just to see where it went.
Oh, okay. I'll take this back. So that's 30. Would this fire to cone 10? Yeah. I mean, it probably would. I mean, it wouldn't kill you to take the clay level down to 6 and the flint down to like 25. You know, that wouldn't be the worst change in the world at cone 10. But yeah, I mean, in general, I think you're probably okay.
Mm-hmm. Okay.
Yeah, that looks pretty decent.
Mm-hmm. Yeah.
But yeah, I mean, those variations are sort of the simpler things you can do.
So I was just wondering about you make those changes and then you've still got the same colorants. So except for the talc and the zinc, the colors should stay relatively similar.
For the most part, especially with the R2Os. With the R2Os, you rarely find a lot of variations in them. Hold on, I'm going to abuse my students from another class because they're wonderful and I love my students. But let me pull up a test I got last week. Oh no, where is it? Hold on. Sorry, talk amongst yourselves while I Google here. Peter. Is that the one? Nope. Oh, come on. Where'd you put it? Where'd I put it? Here we go. Oh, I didn't even want Peters. Did I want Peters? That's lab 1. Where's lab 2? No. And I should stop. I'm just wasting time looking for. But basically, that the short version is, yeah, by changing R2 or R2O source, it's probably it's not going to give you a major change, right? It's not going to give you major variations, and I just can't find the other test I was going to show. So is that universal? There will always be anomalies, like I say, of how some things can happen, but for the most part, that they're fairly interchangeable. Did that answer your question?
I think so.
I got distracted looking for a result to answer your question. I forgot what the question was. Like I said, I'm a little sick.
I have a question about the colorant.
Yeah.
the base, the glaze that I'm using is matte glaze, but most of the test out came out like glossy. So the colorant will actually change the chemistry and bring it to the glossy part of the glaze. Because most really.
Right. It can. Like we said, so you're using rutile as a colorant. Rutile is iron and titanium. They're both a minor amount of flux. Iron or chrome is the big refractory material. They can have some effect, but not a huge effect. Some people will say that copper will really change your flux response, but I mean, yes, to a certain degree, but it's not a huge player. But certainly I think probably the more interesting thing for you would be to take that base and to try a range of colorants on that original base and to see how they affect the system as a whole. And as we said with yours, I think I already overwrote your formula. But that you've also got this wiggle room where you can take out flint and affect the matteness of the glaze and see how that affects colorants. Because again, sort of one thing that we don't talk about extensively, if at all, is that in a matte glaze, the crystals will pick up colorants different than the glass. Okay, because the colorants can incorporate themselves into the glass. We see that more evidently in the crystalline glazes because they're big crystals and you can get separate colors depending on how you colorize them. But in matte glazes, you can get a very similar effect. I'm trying to see if I've got a good picture of it. But like I said, of try all the different colorants is really where you're going to find out more effectively. Sorry, I'm looking for a picture here. I have too many pictures, too many files. Can't keep track of everything. Well, this is the crystalline example. I showed this one, but this isn't even like, whoa, that's just because of nickel, right? And I mentioned how these crystals are blue because there's cobalt present in nickel. They just naturally occur together and you can't separate them out. And so, it becomes very hard to, so the glaze picks up one and not the other. So yeah, can you guys hold on for 1 second? I have to go check on my kids. Okay. I'm going to turn off the mic and the camera, but I'll be right back. Okay.
I got a question for you guys. Have any of you guys ever seen a glaze? And maybe I did understand it right, but it looked to me like the glaze was corrosive to the clay body underneath it in some places, and it like took out chunks of clay. And I don't know if maybe it was just what the person had created otherwise, in the initial piece of work before the glaze was applied. Any of you guys ever seen that? I'm trying to look for a picture.
I think glazes like that are called sacrificial glazes, where there's like a flux that attacks the silica in the clay body to form the glaze. I think that's how soda fires and salt fires work, actually, is that the sodium flux pulls silica out of the clay body and sort of eats into the surface to form a glass.
Say that again.
Well, I was asking them about something else. Because I saw a piece that looked like it had some chunks taken out of it, and I thought that it was the glaze affecting the underlying clay body. And he brought up sacrificial glazes as maybe pulling the silica out of the clay body. To me, it looked like the pits were pretty deep, and I don't know if we're talking about the same thing.
Where was this image? Or it was a pot you saw?
Yeah, it wasn't it was a piece, but yeah.
I've seen copper carb corrode into a shelf before, like through the through the kiln wash, and we had to grind the shelves down. And I think
Why-
it was just a big concentration. I don't know. It was
I
kind
was
of
going to say, why was there so much copper carb?
it was a bad experiment.
Well, there's no such thing as a bad experiment. There's just a lot of grinding of shells to be done.
Yeah.
I mean, a lot of copper carb is not, necessarily safe or stable, but it could certainly be interesting.
It was put in a little dish to volatilize in the kiln, and it really just went to the most immediate spot. But it did. It must have bubbled over or something. I don't know, and went on the kiln shelf and kind of did some damage.
So it was pure copper carb.
It was, with water, a mix, just, yeah.
But it was in. I'm sorry. It was in a.
It was in a shell. It was in a shell, like just poured in a shell and set down on the kiln shelf.
And so you're trying to fume with it.
Yeah.
Oh, interesting. But it burned through the shell, or bubbled over. It
Bubbled over, and he was asking about corrosive results. That was pretty corrosive.
Man, is this what you all do at Watershed when no one's looking?
Yeah, when Reed's not there.
Oh my goodness. Bunch of troublemakers. Yeah, I mean, you overdo anything and it will certainly overdo itself. Yeah, I mean, as far as Jeff's original question, I couldn't really speculate without knowing more, but
I'll try to find it while we're still on the phone. But.
yeah.
I do have a question about durability or stability.
Mm-hmm.
I have a recipe that I want to try for a slip, and I did look at the numbers just out of curiosity. I mean, it's not a glaze, but do you try to stick to the same 0.3 to 0.7 for a slip with colorants?
No, with slips, the rules sort of go all out. The UMF rules, and this goes back to clay bodies as well. The UMF rules don't really apply. Actually, they don't apply at all to clay bodies. Okay. And a slip is really just a clay body that, you're putting in a liquid form. Sometimes you get slight variations here or there. Now we can plug a slip into the UMF calculator, but you'll see very quickly what happens is the numbers go pretty wacky. The first thing is, like I said, in a clay body, you only have an alkali metal flux. Okay. There's no alkaline earth in a clay body. For the most part, there's a few special exemptions here and there, but for the most part, it's all alkali metal. Well, how can you have that when all I say is you need these two to be stable? And that's because there is so much silica and alumina that you just tie up all of that alkali metal. So, here is Val Cushing's Cone 10 slip as UMF. It's basically all alkali metal. There's some trace alkali earth, but basically it's all alkali metal. But the alumina level is 4.9. I mean, it's almost 5. Right, the silica level is 19. These numbers are so huge. Remember, Stull stops at 7 silica and 1.0 alumina, right? So the numbers really go out of whack as far as stability and all of that kind of thing. An ongobe is a slightly more vitrified slip. Ongobe formulas are lower amounts of silica and alumina. So, here we're at about 2 alumina, 11 silica, and an ongobe All the ones that I've ever collected will have a small amount of boron added in them too, so it's a more vitrified slip. But again, it's not melting at all. High amounts of alumina, high amounts of silica, some boron, all alkali metal. So
the formula that I have has a 3-to-1 silica alumina ratio and a 0.07 to 0.93 R2O to RO.
It's 0.93 RO.
Yeah.
Do you mind sharing the formula?
Yeah, it's 50, and I haven't tried this. This is just the recipe I copied, but 50% kaolin.
Any kaolin or just
said kaolin. 17 feldspar. Yeah, I haven't completely deciphered this. 33 whiting.
Give me 1 second. 33, 17 feldspar. I'll just go with soda spar since I assume. Minspar 17. Any flint?
It's
No, that's
kaolin,
100.
feldspar, and whiting.
That equals 100. Wow, that's wacky. I've never seen a slip formula like that.
And then it's 1 to 2% of a colorant, like I think copper carb was. Let me take a look at what it was. Cobalt oxide. So
I mean, I rarely say this, but
Yeah.
I have no idea what to make of this formula. I'll usually go ahead and speculate and bullshit my way through a discussion, but I really don't know what to make of this. I mean, I can't say good or bad or whatever. I have never seen a formula like this.
This is this artist that I've followed on Instagram, Elise Helen
Oh, I actually know Elise L. Hansen.
Yeah, she has this beautiful slip, and she's given the recipe for it, and the formula, and this is it. Now, you know, maybe she didn't really want to give her formula, but there you go.
I mean, I've never looked at Elise's formulas before. Yeah, I mean, is it a slip? Sure. What is this going to do?
Well, it changes from, depending on whether it's in oxidation or reduction, whether it's, these beautiful chartreuses or,
Wait, what colorant did you say it was?
Well, let me see what, I've seen notes for 1% cobalt oxide or 1% black copper oxide.
Lisa, all I can say is I want you now to try this. And
I'm trying to try it. I just haven't gotten to it.
I want you to I want full documentation.
I don't know if I can show you a photo on
You should be able to do it. You should be able to do a screen share. Oh, you got it on your phone.
You can't see this. Oh.
I just get a lot of shine back.
I don't know how to get a picture up on there.
Is that an atmosphere as well?
This might be a reduction firing, but or this, she does this in an oxidation as well.
I mean, if I had to lay my definitions, I mean that's a glaze, not a slip. But you're right; it's got 50% EPK, so it's going to be thick and funky. But I mean, this.
I'll email some photos to you, and I mean maybe you'll pick them up right now.
You can share them through through Google Drive within the application. So I just shared an image by opening up the group chat and then clicking on the little icon at the bottom that says choose. It looks like a little triangle.
Is the group chat over there on the sidebar or what?
Well, if you click on the blue icon on the far left, then
it's not going to let me.
On the far right.
It's not going to let me open it though.
You know,
'cause
I'm not.
I've got multiple Google accounts. You can email it to me, Lisa.
Okay.
Oh,
I'll
did you
send
try
it right
opening
now.
that thing and it didn't open?
Well, it's because I have multiple Google accounts.
Oh,
So like I use one account that's running this. I've got like 24 Google accounts.
that's interesting.
Yeah, it's complicated.
Okay. Well, I'm sending it to you right now.
Yeah,
And maybe you'll get it while we're on the phone, while we're here.
sure.
So what? So did you say that the way I sent it didn't work? You tried clicking on
just
that image?
It didn't work for me.
Well, because I wanted you to discuss that picture in a minute.
Oh, okay. No, it says I need permission.
Yeah, me too. I can't open it.
Yeah, it says, do you want in, ask for access, or switch accounts?
Yeah.
Okay.
So if I click request access, it says your request for access has been sent. You'll
Oh.
receive an email if or when your request is approved.
Okay. I just got the requests.
All right, I probably
Boy.
sent 3 of them to you now.
Okay.
Okay. Well, I just emailed that to you, so maybe you can
Okay.
pull them up.
Came through on my phone. So just give me a second. It'll show up on my email. There we go. Okay.
There you go. Yep. Now that she's done some layering there, but that's the slip.
Can I zoom in here? View.
There's one of 2 pictures which really shows it nicely. There you go.
I mean,
So she used cobalt there,
yeah.
but that's it.
It looks like it's mostly in the application.
Well, she said the thickness affects it.
Well, it looks like it's directionally sprayed.
Yeah.
So, not the whole thing sort of evenly homogeneously sprayed.
Do you know what temperature they're fired to?
10.
I don't. Let's look at this formula again. I mean, it's a slip because it's got so much clay in it. I mean, again, sort of talking about the anomalies of how these things work, because from a chemistry perspective, if we just take the clay out, right? This is what happens when you've got a lot of RO because it doesn't have any silicon aluminum attached to it. Well, they overcame this by having 50% clay. But is it melting? Is it vitrified? Will it stick? Sure. What effect it will have on color? I mean, like, I would bet that that's copper. That might be black copper oxide. That might be copper carbonate. And I'd probably say we've got cobalt, and maybe the yellow is iron. And then that looks like the natural clay. I guess the black could be. No, the black is probably copper oxide. I learn something new every day. You got me, Lisa. I don't know.
Well, I guess my question about it was is say that's on a mug, like the lip of a mug. Is it safe? The colorant is secure in there. It's not going to leach out, or is it stable?
I again,
You can't answer that.
I cannot answer that in the slightest. I have no idea what it's doing chemically. Like I said, I mean, my response is I want to say it's a matte glaze. Because I have made this glaze in the glossy region, and I have made glossy glazes at cone 10 only flux with calcium. I have done that before. You can make that happen. So if that works, theoretically, this is somewhere between either an actual mat, underfired, or as we were talking about with the Shinos, when you go all one flux, right? Which essentially this min spar is really just for show. As you go all one flux, how do the rules apply? And I will admit that is one thing I have never done. I have never recreated Stull using only calcium. So I don't know.
So
like
if you added some flint to that, it would move it over a little bit in a little.
Theoretically, it should. This then has a second problem because, like I said, looking at those pictures, okay, so we had some flint. That's at 20% flint. See, that doesn't even do it. 30, 40. It now comes down into an application issue again of there is so much clay in that formula. Again, now does the physical property of the clay change its performance? Does that make it a slip? Does it melt? Does it not melt? Do the rules of mat apply? Try this with the flint.
Mm-hmm.
I mean, you know what the rules should be.
Yeah.
But you're like out there right now. You're like,
yeah, well, I was about to pull together some tests and fire them both in reduction and in oxidation and just see what happens, I think it's beautiful. I just, want to make sure it's going to work.
yeah, I mean, okay, so going back to the question, like if you had to put your money on whether or not this would be quote unquote food safe, I probably wouldn't put that gamble.
Yeah.
Just as a CYA. Cover your posterior.
Mm-hmm.
It could be. I literally actually, while we've been in class, one of my stop it, mouse. Stop it, bad mouse. Stop it. One of my Alfred students just emailed me and he's like, "Hey, what should I do for research this semester?" I don't know. Maybe I'll have him do this because I don't know. You try it and you report back.
I will. Well, in her notes, she says it's something she learned in college. She calls it Malt B 123, and she's been using it since the 70s. And
MALT.
MALTBY, Malt B.
TBY.
Yeah.
Food bank. Brighton area schools.
Well, it was an English art school, I thought.
Yeah. She's Danish, I believe.
Yeah.
If I remember correctly. Anyway, it's okay. Try it and see. Good way to round off a class. I have no idea. I show all these results. I can show you. Oh my God, you guys, look, I'm so amazing. All this stuff I'm showing you works. I haven't been teaching you lies. And then Lisa makes it awkward. There you go, Lisa. You just ruined everyone's class.
I have a question. How do you define a glaze from a slip? Because the recipe is telling us it's a slip, but then you're saying that it's a glaze. So
Well,
how do you define it?
That's part of that's part of why I'm sort of having this existential crisis with this particular glaze, slip, whatever. Okay, I mean, what's a slip? We can come in here, and here's a slip formula. It's 70% clay, Nephsi, and flint. Right, here's another one. That's the same thing. 70% clay, nepsi, and flint. Let's pick someone else's. Okay, so this one is 65% clay, Kona F4, and flint. As I was saying, slips are really just liquid clay bodies. Sometimes they'll have more flux than a traditional clay body, but slips don't melt for the most part. Okay, so they're not glassy. They will have some texture to them, but they're not melted, food safe, vitrified, all of that for the most part. It depends on the composition. I was talking briefly here about ongobes. Ongobes are slightly more fluxed, but I wouldn't necessarily call them vitrified. But again, these have slight anomalies that we escape from glazes. They have all alkali metal and very little to no alkali earth. This formula that Lisa's got is just nuts because it's all alkali earth, no alkali metal, a lot of clay. So like it does have a fair amount of clay, so it sort of fits into the roles of slips. It also fits into the role of glazes. So, I don't have an answer. Generally, though, a slip will have a lot of clay. We talk about that a glaze, you really can't have more than 30% clay because it's too physically thick. Your silicon alumina levels get too high and it dries up. Slips, that doesn't really matter because it's really just liquid clay. So it's an opaque surface. It can be used to hide the underlying clay body, to say, let you throw with the stoneware and you put a white porcelain slip over it and it gives you a white appearance for your glazes. The definitions of slip are somewhat malleable, but they're fairly well defined as to generally what you want. High clay, no alkali, no alkaline earth. So let's jump to Jeff really quick. So you want to talk us through these?
Well, this isn't what I was looking for, but this is something that is not too different from what I was thinking. This looks to me like maybe a thick slip that was applied on top of or I don't know if you call this a slip or a glaze. On top
Are you talking about the cracking?
The cracking. Mm-hmm. If you look at it from the side, you can definitely tell that it's a different clay body on top. And I don't know what that is. That to me looks like it's just something that was that constricted.
Yeah.
And that's it. I mean, just like maybe they applied maybe something, a clay body with a little bit of flux in it to, on top of their, it probably would have been a bisque piece, you think? Or I don't know.
Do you know if this goes onto the underside as well, or if it's just on top?
It's just on the surface. Yeah.
Right. See, yeah, I would bet it's a slip, maybe an on-go, but it's a high clay suspension that shrinks and then bonds to the surface. And that's why I ask if it's on the underside, because if it doesn't bond particularly well, stop it. Stupid mouse. It would flake off on the underside.
So this is another view of it.
It's probably more on the on-gobe. Yeah, so yeah, you can see the underlying clay body. It might be more of like a high clay on-gobe, so that the on-gobes are slightly more melted, so they stick a little bit better. But that, yeah, I mean, it's basically the same thing that I talk about with the crawling glazes. It's just this never melts. It just crawls and sticks in place, or shrinks and then sticks in place. Neat effect. I can't say I've seen someone do that before. I may have, but
well, it kind of has a glossy surface to it. Is that sort of part of the transition that you'd see in a partially fired glaze? That, well, I mean, this is one that's shrinking, but I guess when I looked at the piece we were talking about, when mine didn't have grossly borate in it, it was very matte, and it had some specks in it where it looked open, like, but it sure didn't stay as cohesive and crack.
Right. Well, okay. So here, so here's an on-gobe formula, right? And what you've got is it's a whole bunch of fluxing. I don't really care about that. What you've got is you've got three clay sources here. You've got EPK, right? You've got OM4, and those together are only 20%. And then you've got 20% calcined kaolin. Now, the benefit of calcined kaolin is that it doesn't crack. Or, I'm sorry, it doesn't shrink. And so you can use it with less shrinkage. Okay, the material itself won't shrink. Now, if we flip that on its head and made this all whatever Graulig or some other regular kaolin that's not calcined, it would shrink. But the glaze would have the slip would have the same basic melt, where it's probably going to be melting, but not particularly well melted. So something like this might say, with regular kaolin instead of calcine, would probably have that same effect, where it would shrink, and then when you fired it, it would be fired into a semi-permanent state, but it wouldn't necessarily be, there to stay, or it wouldn't be melting in an active way, but melting enough to stick.
Yeah. Okay, thanks.
Okay, sure.
I had a quick question about bloating in
Go
clay.
for it, Michelle. A
What's that?
clay question. Oh, I shouldn't answer clay questions. This isn't
But
the
what's
clay
happening?
class.
Oh.
Go ahead.
No, just like like bloating. When bloating happens in clay, like what is that? Is that gas, or like the iron?
Well, there's multiple reasons that bloat happens. One is yes, iron will cause bloat. In the clay flaws section, I talk about how gas release doesn't cause pinholes, right? And I showed those documents that show the gases being driven off from calcium carbonate and all that. There is one material that does give off gas at high temperature, and that is iron. Okay. Around cone 4, red iron oxide will naturally degrade into black iron oxide, and it will give off oxygen as a result. And cone 4 happens to be within that 6-cone melting region that I talk about, that our glazes aren't actually melting for those last 6 cones, and our clay bodies are around that same sort of area. That last 6 cones is really where things are melting. So if you have iron, and specifically you have to have a fair amount of iron, at least over 4% iron in your clay body, the red iron oxide will convert to black iron oxide over cone 4, and that can be released as a gas, and it can cause bloating. Now, what most people do that have high iron clay bodies is this step called body reduction. Body reduction is a reduction around cone O10, so very, very low. And what it is attempting to do is to pre-convert that red iron oxide into black iron oxide earlier in the firing before the glass forms. It mostly works, doesn't always work. Okay. But, I mean, are you talking about bloating in a red or brown body?
Yeah.
Yeah. Then you're getting you are getting iron degassing.
Mm-hmm.
Do a body reduction. So or are you firing in gas kilns?
No. So if it's in oxidation, I guess like you can't really avoid it, right?
Not really. Is this in like your dinnerware? Like you're seeing bloats on plates?
I've just seen it happen like maybe 1 or 2 times in like a planter that I made. But other people were saying, that they've experienced a lot of bloating with this type of clay. And it's like a lot of iron in it. So
right. I am not a fan of picky firings, but you could try to dwell around cone 04 and see if that'll make the conversion happen while you stay at that temperature before you form a lot of glass. There's no guarantee that that's going to solve your problem, though. I mean, yeah, it's one of those things that there's really not a particularly good answer if you're in oxidation.
Is that typically a problem for like earthenware? Like,
Well, most earthenware is not going over cone 04.
oh, right.
Now, what you will find is that there are a lot of chocolate bodies or dark bodies near black bodies that will fire to cone 10, but they're almost always done in reduction. And it's just to force that conversion. If you're stuck in an oxidation kiln and you really want a dark appearance, honestly, I'd go back to the slip conversation. I'd say use whatever clay you want and put a red slip over it, and most likely the red slip will be okay. But yeah, it's I don't have a good answer on how to get rid of that in an iron bearing body.
Okay.
It's a bummer. And that's one of those things of, I love to tell you that all the answers are there, but sometimes, you talk, sometimes you ask a question and the answer is no. I keep telling that to my son. Yeah, you can ask for ice cream, but sometimes you ask and the answer is no. Yeah, it's a problem. Iron is a problem. It's a major challenge. Yeah, sorry. I'm trying to think if I can figure one positive spin to put on it, but I don't have one. So. Any other questions?
The picture that Jeff was showing, the crackle, I've seen a similar texture before. If you're throwing and you put sodium silicate on the outside of a pot.
Yeah.
Could that be something like that? It's just it's got to be stretched though.
Right, that's the whole thing of with the sodium silicate, you're actually dispersing the outer layer of your clay. And then you're forcing it apart, so it's separating. I mean, it could be something like that. I mean, one way or another, it's just you're forcing a layer of slip to crack, and then you're firing whatever the composition enough is to stick. How they get it, it could be sodium silicate. I'd bet it's just a high shrinkage clay because at least that'll stick on its own. It'll bond pretty well. But yeah, I mean, there's a different ways to do it. But that's a good thought.
I had one question.
Okay, I have one answer.
It's a grade question. I am having a hard time finding my grades, and I don't know if this is a me problem or me not knowing how to use Alfred.
It's a you problem. You got. Oh, I'm not allowed to say. Sorry, you did fine.
Well, where should I be able to find it?
Again, here's where the discrepancy lies. I don't know what students see, what versus I see. The straight up answer is contact the registrar.
Okay.
It should be inside Banner. So if you go to myalfred.edu, one of the tabs is Banner. And you can log in there. But as you're going to have to get your credits transferred, you're probably going to have to contact the registrar anyway.
Okay, I can just call them tomorrow.
Yeah, and that's, if I remember correctly, it's 607-871-2123.
Okay.
But yeah, you did fine.
Also, Blair said hi to you too. I'm in his class now.
Oh, hi, Blair. Tell him I'm going to talk to him at Ensika. I have to talk to him, so I'm going to find him and talk at him. Okay, good. Tell him give him my best.
Okay.
Yeah, he'll be a lot of fun. He's a good guy. You guys, this has been great. You've been a fun class. I know it's been compressed and smushed, but I hope everybody's learned a lot. I mean, that's always my goal, is to fill your brains with knowledge. So now you only have more questions, and you don't really know where to go with it. I do have a request. It might be a little bit late, but I forgot to announce that there are course evaluations on Canvas. and I don't know whether you have access to Canva still. It's sort of acting crazy. Even if you don't have it, you can contact the department administrative assistants, which is a woman named Billy Burns, which is just BURNS at alfred.edu. And she administers them. And if you really love the course, I would appreciate if you wrote the department. .edu. My department chair is Linda Sikora, and it does not hurt for people to say how much they enjoyed my experience or their experience with me. Linda's email.
So I tried doing the Alfred U one, but that one closed when the grading closed. So I will do one of the other methods.
Yeah,
but
contact Billy. You know, if you really enjoyed the experience, Linda Sikora is my department head, and that doesn't hurt.
And Burns at alfred.edu.
Yeah.
Who is that?
That's Billy Burns, Billie. She's the departmental head administrative assistant. I put them in the chat here if you've got the chat open. You know, I love doing this. I love, you know, the cool thing is how many people we can get out there in touch of. You know, we've got people here from Maine to Virginia to New York to Hong Kong to San Francisco. It's really amazing. Summer school just went up yesterday. Glazes 2 and clay bodies will be offered in summer school if you're interested in those.
What are the dates of that?
Oh, I just got that this evening. It's the 20. Where is it? Hold on. It's the 29th of June. Hold on. Where's that email? We're gonna find it. June 26th through August 4th. So it's a slightly longer session. Is that 6 weeks? So it's a little bit more relaxed. I will say something after. Are we all done? Actually, I'll stop recording here if you guys are all good.
I just sent you another email with a photo in it.
Oh yeah, turquoise, copper.
I was listening to that Glaze Effects video, and I realized I had that sitting behind me.
You're now going to be haunted by all the tricks that you see that people are doing for glazes. Like you're not going to be able to escape. You're going to be like, I know what you're doing.
I had to get out of that glaze group on Facebook. It was driving me crazy.
Which one?
I think it's just glaze recipes.
Hold on. Okay, I'm going to stop recording here so I can gossip. Okay. Hold on.